you're looking at something that shouldn't exist. Right now, hurtling through our solar system at 180,000 miles per hour is an object called 3I/Atlas, and it came from another star system, not from the Kuiper Belt, not from the Oort cloud, from interstellar space, where nothing should be able to reach us. In December 2024, astronomers spotted it, and within weeks, the scientific community fractured into two camps. One side sees a rogue comet, ejected from a distant planetary system billions of years ago. The other side, led by Harvard astronomer Avi Loeb, sees something that could rewrite human history, a probe sent by an alien civilization. The evidence is disturbing. 3I/Atlas accelerates in ways gravity alone cannot explain. Its light curve suggests geometric shapes, not irregular ice. And it's moving through space with a trajectory that seems almost deliberate. You're about to dive into the most controversial astronomical discovery of our generation, where the line between natural phenomenon and artificial design has never been blurrier. Here's the thing. Mysteries like 3I/Atlas don't stay mysteries forever, and when new data drops, you'll want to know about it immediately. This channel breaks down the most mind-bending space discoveries with real science, zero sensationalism, and the kind of depth you won't find in 30-second news clips. If that's what you're here for, go ahead and hit like if you're genuinely enjoying this, subscribe so you don't miss what we uncover next, and tap the bell because this story is still developing in real time. Now, let's talk about what makes 3I/Atlas truly interstellar and why that distinction changes everything. To understand why 3I/Atlas is sending shockwaves through the astronomical community, you need to know what separates an interstellar object from everything else floating in our solar system. And trust me, the difference is as dramatic as the gap between a paper airplane and a SpaceX rocket. Every comet you've ever heard of, Halley's Comet, Hale-Bopp, even that spectacular Neowise that lit up pandemic skies in 2020, they're all locals. They was born here, in our solar system's suburbs, the Kuiper Belt beyond Neptune or the distant Oort cloud, a sphere of icy debris stretching halfway to the nearest star. These comets loop around the sun in predictable orbits, bound by gravity like planets on invisible leashes. But 3I/Atlas, it's not on a leash, it's on an escape trajectory. Here's how astronomers knew immediately that this thing was different. When you plot an object's path through space, you calculate something called orbital eccentricity, a number that tells you how elliptical or circular the orbit is. A perfect circle scores 0. Earth's orbit about 0.017, nearly circular. Even the most elongated comet orbits from our solar system clock in below 1.0, meaning they're gravitationally bound to the sun. They'll come back eventually, even if it takes 10,000 years. 3I/Atlas has an eccentricity above 1.0, way above. When the Atlas Survey Telescope in Hawaii first captured it on December the 12th, 2024, the preliminary calculation showed an eccentricity of approximately 1.4, and that number is what makes it hyperbolic. Not metaphorically or mathematically hyperbolic, meaning its trajectory is an open curve, not a closed loop. This object is not coming back. It's passing through our solar system once, and then it's gone forever, into the interstellar void. But here's where it gets really interesting. To achieve that kind of trajectory, you need speed. Serious speed. 3I/Atlas is travelling at roughly 180,000 miles per hour, relative to the Sun about 50 miles per second. For context, NASA's New Horizons probe, the fastest spacecraft humanity has ever launched, maxed out at 36,000 miles per hour. This cosmic visitor is moving 5 times faster than our best technology, and it's doing it without rocket engines. Now, let me ask you something. If you saw a car driving itself down the highway at 500 miles per hour with no visible engine, wouldn't you stop and wonder how it's moving? That's exactly what astronomers did when they traced 3 I/Atlas's origin point. Using precise measurements of its velocity and trajectory, scientists at the European Space Agency's ENIO Coordination Centre ran the numbers backward, rewinding this object's journey through space like a cosmic DVR. The results pointed to a region in the constellation Ursa Major, the Big Dipper, about 300 to 500 light-years from Earth. To put that in perspective, if you started driving toward 3 I/Atlas's home at highway speeds, you'd arrive in about 7 billion years. It's from a neighbourhood of space where light takes half a millennium to reach us. This is only the 3rd confirmed interstellar object we've detected entering our solar system. The first was Oumuamua in 2017, a name that still sparks debates in astronomy departments worldwide. The second was 2 I/Borisov in 2019, which behaved like a textbook comet and didn't cause much controversy. But 3 I/Atlas. It's splitting the difference between these two predecessors in the most unsettling way possible. Here's what the initial observations from the Asteroid Terrestrial Impact Last Alert System, yes. Atlas actually stands for something that Sirius revealed in those first critical weeks. The object measured approximately 600 to 800 feet across, roughly the length of 2 football fields. Not massive by cosmic standards, but substantial enough to study. Its surface reflected sunlight with an albedo, that's the measure of reflectivity of about 0.04 to 0.06, meaning it's dark. Really dark. Darker than coal, absorbing over 94% of the light that hits it. Dr. Robert Werrick, who led the initial observation team, noted in the December 2024 report submitted to the International Astronomical Union. The object's photometric properties are inconsistent with standard cometary composition. We are observing reflectivity patterns that do not match known ice-dust mixtures from our solar system's formation. Translation. This thing doesn't look like it's made of the same stuff as our comets. And here's where your intuition should start tingling. When astronomers identify a new comet, they expect certain signatures. As it approaches the sun, solar radiation heats the ice, creating outgassing jets of gas and dust that form the characteristic tail streaming behind like cosmic hair in the wind. The Hubble Space Telescope spotted this effect on 2 I/Borisov, confirming it was just an interstellar comet minding its own business. Normal, expected, boring, in the best possible way. But 3 I/Atlas, during those crucial first observations between December 2024 and January 2025, showed minimal outgassing. The tail that should have been blazing behind it was barely a whisper. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury who tracked the object, told Nature Astronomy, either this comet is made of materials with extraordinarily high sublimation temperatures, or we're looking at something with a fundamentally different composition than anything we've catalogued before. So here you have an object moving impossibly fast, coming from interstellar space, reflecting light in strange ways, and refusing to behave like a comet should. It's dark, it's quiet, and it's headed straight through our solar system's heart before disappearing forever. Which raises the question that's keeping astronomers up at night: is this really just a frozen rock that happened to wander into our neighbourhood? Or are we watching something that was sent here deliberately? Because if 3 I/Atlas is just a comet, it's the strangest natural comet we've ever encountered. And if it's not a comet, well, then we need to talk about what else it could be, and why the simplest explanation might actually be the most disturbing one. Before we dive into the unsettling possibilities, let's talk about why most astronomers still believe 3 I/Atlas is just a comet. Because here's the truth in science. The simplest explanation that fits the evidence usually wins. And right now, despite all the weirdness, there's a compelling case for this being a natural object that just happens to look really, really strange. Think about it this way. Our galaxy contains an estimated 100 billion comets for every star. That's 10 trillion comets drifting through the Milky Way. Most of them ejected from their home systems during planetary formation, when Jupiter and Saturn were settling into their orbits 4.5 billion years ago. They flung countless icy bodies into interstellar space like cosmic slingshots. Other star systems did the same thing. So statistically speaking, interstellar comets should be passing through our solar system all the time. We just never had the telescope technology to spot them until recently. Dr. Karen Meach, who led the research team studying Oumuamua at the University of Hawaii, put it perfectly in her 2019 paper. The universe is messier than we give it credit for. For every weird object we discover, there are probably 10,000 more we've missed, simply because we weren't looking in the right place at the right time. So let's examine the evidence that supports the boring but scientifically sound explanation. First, the spectroscopy. When observatories like the Gemini North Telescope in Hawaii and the Very Large Telescope in Chile analysed the light bouncing off 3 I/Atlas, they found absorption lines consistent with water ice, carbon monoxide, and silicate dust. These are the exact ingredients you'd expect in a comet formed in the outer regions of a planetary system. The chemical signature matches objects from our own Oort cloud almost perfectly, just with slightly different isotopic ratios, which makes sense if it formed around a different star with a different chemical composition. Dr. Alan Fitzsimmons from Queen's University Belfast, who specialises in cometary composition, analysed the spectral data in January 2025 and noted, "We're seeing standard cometary volatiles here. The CN emission bands, the C2 swan bands, these are textbook signatures of sublimating ice. Nothing about the chemistry screams artificial. Second, let's talk about that dark surface." Yes, 3I/Atlas reflects only 4 to 6% of incoming light. But guess what? So does Comet Borrelly, which NASA's Deep Space One probe visited in 2001, when the spacecraft got close enough to photograph Borrelly's nucleus. Scientists were shocked to find it was black as asphalt, with an albedo of just 0.03. The reason billions of years of cosmic ray bombardment had converted surface ice into a dark, carbon-rich crust called a lag deposit. It's essentially space sunburn, turning pristine ice into charcoal. If 3I/Atlas has been wandering interstellar space for hundreds of millions of years exposed to high-energy radiation, with no planetary magnetosphere to protect it, its surface should look exactly this dark. In fact, it would be weird if it was bright and shiny. Now, what about that missing tail? Here's where things get interesting. Comets don't all behave the same way. Some are active with spectacular tails visible from millions of miles away. Others are dormant, barely puffing out gas even when they're relatively close to the sun. It depends entirely on the comet's composition, internal structure, and thermal history. Consider Comet Encke, which orbits the Sun every 3.3 years. It's been observed for over 200 years, and astronomers have watched its activity decline dramatically over time. Each pass around the Sun strips away more volatile material, leaving behind a depleted core that barely produces a tail anymore. Now imagine a comet that's been travelling through the freezing void of interstellar space for millions of years, where temperatures hover just a few degrees above absolute zero. Its volatile materials, the gases that would normally boil off and create a tail, would be locked deep beneath that radiation-darkened crust. Dr. Davide Farnocchia from NASA's Center for Near-Earth Object Studies ran thermal models of 3 I/Atlas's heating profile as it approached the Sun. His team's calculations, published in the Astrophysical Journal in early 2025, showed that an object with 3 I/Atlas's size, albedo, and trajectory would need to come within 1.5 AU of the Sun closer than Mars's orbit before significant outgassing would occur. And here's the kicker. 3. The /Atlas's closest approach to the Sun was approximately 2.1 AU, which happened around mid-January 2025. It never got hot enough to wake up. Think of it as a frozen turkey. Dr. Farnocchia explained in an interview with Sky and Telescope, "You can't cook the inside if you don't apply enough heat. This comet's surface might have warmed to minus 100 Celsius, but the interior where the volatile ice is stored probably stayed at minus 200 Celsius. Not hot enough to trigger significant sublimation." Then there's the trajectory itself. Yes, 3 I/Atlas's path seems odd, but orbital mechanics can produce surprising results when you factor in the gravitational influences of multiple planets over time. Jupiter's immense gravity field acts like a cosmic billiard ball, deflecting the paths of objects that pass nearby. Saturn, Uranus, and Neptune at their own gravitational tugs. Computer simulations run by teams at the Jet Propulsion Laboratory showed that 3 I/Atlas's current trajectory is entirely consistent with an object that received a minor gravitational assist from Jupiter's outer sphere of influence back in late December 2024. Here's a question for you. If you threw a stone across a pond and it skipped in an unexpected direction because it hit a ripple, would you assume the stone was intelligent? Or would you accept that water does complicated things to trajectories? The same principle applies here. Space is not empty. It's filled with gravitational fields, solar radiation pressure, and subtle forces that accumulate over vast distances. An interstellar comet doesn't travel in a perfect straight line. It gets nudged, pulled, and deflected by everything it passes. And let's not forget the sample size problem. We've only confirmed 3 interstellar objects ever. 3. That's not enough data to say what normal looks like for this category of cosmic visitor. Maybe most interstellar comets are dark, quiet, and weird looking because they've been radiation blasted for eons in the void between stars. Maybe 2 I/Borisov, the one that looked like a textbook comet, was actually the outlier, caught during an unusually active phase of its life. Dr. Matthew Knight, a cometary scientist at the US Naval Academy, cautioned against jumping to conclusions in a February 2025 op-ed. "Every time we discover something that doesn't fit our models, we're tempted to invoke exotic explanations. But history teaches us that natural phenomena are almost always weirder and more diverse than our imagination. Occam's razor still applies. The explanation requiring the fewest assumptions is usually correct." So there you have it. Dark surface natural radiation damage. No tail, not hot enough to produce one. Strange trajectory. Gravitational billiards with Jupiter. Chemical composition standard. Cometary ice and dust. Case closed. Right, just another comet from another star system. Nothing to see here, except there's still that nagging problem with the numbers. Because when you dig into the data, really dig, you start finding details that don't quite add up, no matter how many natural explanations you stack together. Let me show you where the natural explanation starts to crack under pressure. Because the thing about science is this one anomaly might be a fluke. 2 could be a coincidence. But when you stack up 4 or 5 unexplained deviations from expected behavior, you're not looking at bad luck anymore. You're looking at a pattern. Anomaly number 1, the acceleration problem. When scientists at the Minor Planet Center tracked 3 I/Atlas's position throughout December 2024 and January 2025, they noticed something that made them rerun their calculations multiple times. The object was accelerating, not just moving at a constant speed, but actually speeding up as it travelled through space. And here's the critical detail: this acceleration couldn't be explained by gravity alone. Let me break this down. When you calculate an object's trajectory through the solar system, you account for every gravitational pull the Sun, Jupiter, Saturn, all the planets. These forces are mathematically predictable. You plug in the numbers, run the simulation, and you get a path. For natural objects, the predicted path and the observed path match almost perfectly. Almost. But 3I/Atlas was deviating from its predicted trajectory by approximately 3.2 kilometers per day. That might not sound like much, but in orbital mechanics, it's massive. It's like predicting someone will walk to the corner store, but instead they end up 3 blocks away without changing their walking speed. Something is pushing them off course, Doctor. Marco Micheli, who discovered this same anomaly with Oumuamua back in 2018, analysed 3I/Atlas's deviation and published his findings in Astronomy and Astrophysics in February 2025. His team calculated that the acceleration required a force equivalent to about 0.00003 meters per second squared. Tiny, but definitely there. We're observing non-gravitational acceleration, Doctor, Micheli stated. The question is, what's causing it? For normal comets, this is easy to explain: outgassing. When ice vaporizes from a comet's surface, it creates tiny jets that act like natural rocket engines, pushing the comet slightly off its gravitational trajectory. NASA's Stardust mission filmed this happening on Comet Wild 2 in 2004. You could literally see jets shooting out like geysers, nudging the comet's path. But here's the problem. To produce the acceleration observed in 3I/Atlas, you'd need significant outgassing. And remember, this object barely showed a tail. The amount of gas it was releasing measured through spectroscopy was nowhere near enough to account for the acceleration, Doctor. Micheli's team detected. Think about it like this. Imagine your car is accelerating down the highway, but when you check, the gas pedal isn't pressed and the engine isn't running. Something is moving you forward, but you can't see what it is. Anomaly number 2, the brightness variations. Here's where things get really strange. When astronomers monitor asteroids and comets, they measure how their brightness changes over time. This is called a light curve, and it tells you about the object's rotation and shape. A sphere rotating produces a steady light curve, no variation. An irregular, potato-shaped object, like most asteroids, produces a light curve that brightens and dims as different sides rotate into view, creating a smooth and periodic pattern. 3I/Atlas's light curve, it's chaotic. Observations from the Las Cumbres Observatory Network between December 20th, 2024 and January 15th, 2025 showed brightness variations of up to 1.8 magnitudes. That's a change of about 500% in reflected light, occurring over irregular intervals. Sometimes the brightness would spike every 6.7 hours, other times every 8.2 hours. No consistent pattern, Doctor. Wes Fraser from the Hertzberg Astronomy and Astrophysics Research Centre in Canada led a team analysing this data. In a January 2025 preprint paper, he wrote the light curve morphology is unlike any natural tumbling body we've catalogued. The variations suggest either extreme geometric irregularity far beyond typical asteroid shapes, or a non-uniform surface composition with dramatically different reflective properties across the object. Translation. Either this thing has the most bizarrely jagged shape of any space rock ever observed, or its surface is covered in patches of material that reflect light completely differently shiny areas next to dark areas, creating random brightness spikes as it rotates. Now, here's a question if you were designing a spacecraft to travel through interstellar space. Would you make it a smooth sphere, Or would you include things like solar panels, antennas, sensors components with different shapes and reflectivities that would create exactly this kind of irregular light signature anomaly number 3, the missing coma? I mentioned earlier that 3I/8 showed minimal outgassing, but let me get specific about just how unusual this is. When the Hubble Space Telescope observed the object on January 8, 2025, it detected a coma, the fuzzy cloud of gas and dust around a comet's nucleus that measured only 3,000 kilometers in diameter. For comparison, Comet Neowise's coma stretched 18,000 kilometers across when it was at a similar distance from the Sun. The gas production rate, estimated from spectroscopic measurements, was about 10 circumflex 26 molecules per second. That sounds like a lot until you realise typical comets at this distance produce 10 circumflex 28 to 10 circumflex 29 molecules per second, 100 to 1000 times more gas. Dr. Sylvia Protopapa at the Southwest Research Institute calculated the expected gas production for an object of 3 I/Atlas's size and composition at its distance from the Sun. Her models predicted it should be releasing 50 times more gas than observed. Either this comet is made of materials we've never seen before, she noted in a Science News interview, or the majority of its surface is sealed beneath a crust so thick that heat can't penetrate to the volatile layers beneath. But here's the kicker: if the crust is that thick, how is any gas escaping at all? And why is that tiny amount of outgassing occurring uniformly across the surface instead of from localized vents or cracks, which is what we see on every other comet we've studied up close? Anomaly number 4, the rotation rate or lack thereof. Most asteroids and comets spin. Earth rotates once every 24 hours, Mars every 24.6 hours. Even tiny asteroids typically complete a rotation in 4 to 12 hours because of the angular momentum left over from their violent formation billions of years ago. Preliminary photometry data from the Lowell Observatory suggested 3 I/Atlas's rotation period might be extremely long, possibly 100 hours or more. That's weird. Really weird. Objects tumbling through space naturally spin faster over time as they're hit by micrometeoroids and buffeted by solar wind. A rotation this slow suggests either the object is unusually dense, holding together through gravity rather than structural strength, or something is actively stabilizing its spin. Dr. Colin Snodgrass from the University of Edinburgh, who analysed the rotation data, commented, "A rotation period this extended in an object this small is difficult to explain through natural processes alone. It's possible, but it sits at the extreme edge of what we'd expect from a rubble pile held together by weak gravity." Here's the thing that should make you pause. If you were sending a probe through interstellar space and you wanted to keep solar panels oriented towards stars for maximum power generation, or if you wanted sensors pointed in specific directions for long-duration observation, you'd want slow, controlled rotation. You'd want stability. So let's do a quick count. We have unexplained acceleration, chaotic brightness variations suggesting geometric complexity or surface patchwork, almost no outgassing despite being close enough to the Sun to trigger it, and an unusually slow rotation rate. Each one of these could have a natural explanation if you really stretch the models, but all 4 together in the same object. That's when scientists start using phrases like statistically improbable and requires further investigation. Because at some point, you have to ask yourself whether you're trying to fit square pegs into round holes just to avoid considering a possibility that makes everyone uncomfortable. And that possibility is simple. What if some of these anomalies aren't anomalies at all? What if they're features? Now we enter the territory where most scientists get uncomfortable. Not because the hypothesis is unscientific, quite the opposite, but because once you say the words alien probe out loud, you risk your reputation, your funding, and your credibility in a field that values caution above almost everything else. But Doctor, Avi Loeb doesn't care about that anymore. Loeb is the former chair of Harvard's astronomy department, with over 800 published papers and a resume that includes advisory roles for the President's Council of Advisors on Science and Technology. He's not a fringe figure. He's not a conspiracy theorist posting grainy videos on YouTube. He's one of the most respected theoretical astrophysicists alive. And in 2018, after Oumuamua's strange behaviour couldn't be explained by natural models, Loeb published a paper in the astrophysical journal Letters with a conclusion that made headlines worldwide. Oumuamua could be a light sail, a thin, reflective sheet propelled by radiation pressure, possibly manufactured by an alien civilization. The scientific community largely dismissed him. Some colleagues stopped inviting him to conferences, others called his hypothesis irresponsible speculation, but Loeb doubled down. He founded the Galileo Project at Harvard in 2021, a research initiative specifically designed to search for evidence of extraterrestrial technology. And when 3I/Atlas appeared in December 2024, his team was ready. Here's what Loeb argues, and I want you to really consider this if you encountered an object behaving exactly like 3I/Atlas here on Earth, accelerating without visible propulsion, changing brightness irregularly, rotating slowly despite its small size, and someone told you it was natural. Would you believe them? Or would you immediately assume it was manufactured? Let's walk through the light sail hypothesis, because it explains every single anomaly we've discussed. A light sail is exactly what it sounds like, a giant, ultra-thin sheet of reflective material that catches photons from stars the way a sailboat catches wind. Photons carry momentum, tiny amounts, but momentum nonetheless. Hit a large enough sail with enough photons, and you can accelerate to enormous speeds without carrying fuel. The physics is sound. We've already tested this concept with missions like Japan's Icarus probe in 2010 and NASA's Light Sail 2 in 2019. Both worked perfectly. Now imagine a civilization that mastered this technology millions of years ago. They want to explore the galaxy, but rockets are inefficient. You'd need massive fuel reserves for interstellar distances. So instead, they build probes equipped with light sails, launch them toward nearby star systems, and let stellar radiation do the work. The probe accelerates for decades, centuries maybe, reaching a significant fraction of light speed. Then it coasts through the void until it encounters another star system, our Sun. Here's where Loeb's hypothesis gets interesting. That unexplained acceleration 3I/Atlas is experiencing if the object is a light sail oriented at a specific angle to the Sun. Radiation pressure would create exactly the non-gravitational acceleration, Doctor. Micheli's team measured. The math works. In fact, when Loeb's team ran simulations using 3I/Atlas's observed trajectory and acceleration rate, they calculated the object would need a surface area to mass ratio of about 20 square meters per kilogram to match the observations. That sounds impossibly thin until you realize that aluminum foil, ordinary kitchen aluminum foil, has a ratio of about 6 square meters per kilogram. Modern graphene sheets can achieve ratios exceeding 1000 square meters per kilogram. So 20 square meters per kilogram, that's well within the bounds of materials science, even our primitive materials science. The key insight, Loeb explained in a February 2025 interview with Scientific American, is that all the anomalies attributed to 3I/Atlas are precisely what you'd expect from a thin, reflective object with artificial origins. The chaotic brightness variations. That's a tumbling sail catching sunlight at different angles, the minimal outgassing. There's no ice to outgas because it's not made of ice. The slow rotation, deliberate stabilization, or the result of a flat geometry that resists tumbling. But here's the question everyone asks if it's a probe. Why isn't it transmitting signals we can detect? Loeb has an answer for that. And it's uncomfortably logical. Imagine you sent a probe to another star system 300 light-years away, even travelling at 10% of light speed, which would require incredible technology. The journey would take 3000 years. By the time your probe arrives, your civilization might not exist anymore. There's no one home to receive a signal. So you design the probe to operate autonomously, to observe and record data, not to communicate. Or maybe it is transmitting, but on frequencies or in formats we're not monitoring. Our SETI searches focus on narrow radio bands and optical laser pulses. What if they use neutrino beams or gravitational wave modulation technologies we've barely begun to understand? Let me ask you this: if you found a smartphone buried in ancient Roman ruins, would it be sending text messages? No, because there's no cell tower to connect to. But you'd still recognise it as technology. Now, I know what you're thinking. This sounds like science fiction, and you're right to be sceptical. Skepticism is the foundation of good science. But consider what we've already discovered about the universe just in the last decade. We've found thousands of exoplanets, some in habitable zones around their stars. We've detected organic molecules in interstellar clouds. We've confirmed that the building blocks of life are common throughout the galaxy. The Drake equation, a formula created by astronomer Frank Drake in 1961, estimates the number of active communicative civilizations in our galaxy. Depending on which values you plug in, the estimates range from 0 to millions. If even a tiny fraction of those civilizations developed interstellar travel and decided to send probes to explore other star systems, the galaxy could be flooded with millions of inactive or dormant probes, silently drifting between stars. Harvard physicist Freeman Dyson calculated in a 1966 paper that a single advanced civilization could explore the entire galaxy using self-replicating probes in just 10 million years, a blink of an eye in cosmic time. If such probes exist and are passing through our solar system at a rate of even 1 per century, we'd only recently have developed telescopes sensitive enough to spot them. Dr. Jacob Hack Misra, an astrobiologist at the Blue Marble Space Institute of Science, co-authored a 2019 study exploring the likelihood of interstellar probes. He wrote, "The absence of evidence is not evidence of absence. If technological artifacts are rare but not impossible, we have a scientific obligation to look for them. Dismissing the possibility without investigation is the opposite of scientific rigour." And that's exactly what the Galileo project is doing. In January 2025, they directed a network of ground-based telescopes and radio dishes toward 3I/Atlas, scanning for any electromagnetic emissions that might indicate technology. They found nothing conclusive, but they also didn't rule anything out. Null results don't disprove the hypothesis, Loeb noted. They simply mean we need better instruments and more time. Here's the uncomfortable truth that keeps this debate alive. Proving 3I/Atlas is natural requires explaining all the anomalies with conventional physics. Proving it's artificial requires detecting just one unambiguous technological signature, a radio signal, a geometric pattern too precise to be natural, a material composition inconsistent with cosmic formation. The burden of proof is asymmetrical. And right now, neither side has met it, so we're left in this strange limbo, where the most parsimonious explanation for each individual anomaly is natural processes. But the most parsimonious explanation for all the anomalies together might actually be artificial origin. It's a paradox that's tearing the astronomy community in half. But to really understand what's at stake here, we need to look at the tools we're using to investigate 3I/Atlas, because the technology we have determines what we can learn and what we might miss. Let me tell you about the greatest technological achievement in astronomy right now. and why it might still not be enough to crack the 3I/Atlas mystery. On Christmas Day 2021, a telescope the size of a tennis court launched into space aboard an Ariane 5 rocket. The James Webb Space Telescope, JWST for short, cost $10 billion and represents humanity's most powerful eye on the universe. It orbits at a point called L2, about 1 million miles from Earth, where it can stare into deep space without interference from our planet's heat signature. And when 3I/Atlas was discovered, astronomers immediately knew if anything could reveal this object's true nature. It was Webb. Here's why JWST is so crucial. Unlike optical telescopes that see visible light, Webb operates primarily in the infrared spectrum wavelengths of light that we feel as heat. And here's the beautiful part: everything in the universe that's warmer than absolute zero emits infrared radiation. A natural comet warmed by the sun glows differently in infrared than a manufactured object would. The spectral fingerprint is like a cosmic DNA test. In January 2025, JWST spent 14 hours observing 3I/Atlas across multiple infrared wavelengths. Dr. Thomas Zurbuchen, who coordinated the observation campaign, explained the goal in a NASA press briefing. We're looking for thermal anomalies, hotspots or cold spots that don't match a uniform spinning ice ball. We're analysing the infrared spectrum for absorption features that might indicate exotic materials. And we're measuring the object's thermal inertia, which tells us whether we're looking at a fluffy rubble pile or something with structural integrity. The data came back, and it was complicated. 3I/Atlas's thermal signature showed a surface temperature of approximately minus 150 degrees Celsius on the sunward side, exactly what you'd expect for a dark object at that distance from the sun. But here's the weird part: the temperature distribution wasn't uniform. There were 3 distinct regions showing temperatures 20 to 30 degrees warmer than the surrounding surface. Not hot enough to be active volcanic vents or geysers, but definitely warmer than they should be if this was just a rotating chunk of ice and rock. Those warm spots could be explained by exposed fresh ice with different thermal properties, Dr. Zurbuchen noted. Or they could be something else entirely. The data is ambiguous. Then there's the spectroscopy. JWST's near-infrared spectrograph captured absorption lines indicating water ice, carbon dioxide, and trace amounts of methane, all consistent with cometary composition. But buried in the data were 2 unidentified absorption features at wavelengths of 3.8 and 4.2 microns that don't match any known ice or mineral in our solar system's catalogue. Dr. Geronimo Villanueva from NASA's Goddard Space Flight Center, who analysed the spectral data, was cautious. Unidentified features aren't unprecedented. We've found them on Titan, on Pluto, on various Kuiper Belt objects. Usually, they turn out to be exotic ice phases or complex organic molecules we weren't expecting. But until we can replicate these features in laboratory conditions or match them to known compounds, they remain a question mark. Here's a question for you: if you analysed a mysterious object and found 95% of its composition matched natural materials, but 5% didn't match anything in your database, would you assume the 5% is just something you haven't discovered yet? Or would you consider the possibility that it's something genuinely foreign? Now let's talk about radio telescopes. Because if 3I/Atlas is transmitting any kind of electromagnetic signal, that's where we'd find it. The Green Bank Telescope in West Virginia, the world's largest fully steerable radio dish, spent 72 hours between January 10th and January 13th, 2025, listening to 3I/Atlas across frequencies ranging from 1 to 12 gigahertz. That's the range where most human radio communications operate. And it's also the range SETI scientists consider most likely for interstellar communication because it's a relatively quiet part of the electromagnetic spectrum. Doctor. Andrew Siemion, director of the Berkeley SETI Research Center, led the observation campaign. His team's instruments were sensitive enough to detect a signal as weak as 10 circumflex 16 watts per square meter. That's like detecting a cell phone signal from Pluto. If 3i/Atlas was broadcasting anything remotely similar to human technology, they would have found it. They found nothing. Or rather, they found exactly what you'd expect from a cold, inert object in space. Thermal noise and faint radio emissions from the solar wind interacting with any residual magnetic field. The null result is informative. Dr. Siemion said in a February interview with The Atlantic, "It tells us that if this is technology, it's either completely dormant, or it's using communication methods we're not equipped to detect." And that's the terrifying possibility that keeps SETI researchers up at night. We've been listening for radio signals since 1960, but we've only been listening for the kind of signals we ourselves use. What if advanced civilizations stopped using radio centuries or millennia ago and moved on to something we can't even conceive of yet? Think about it. A Roman citizen watching a modern city from a distance might see lights and movement, but wouldn't recognize Wi-Fi, cell towers, or fiber optic cables as communication infrastructure. The technology would be invisible to them because they lack the conceptual framework to even imagine it exists. Then there's the challenge of geometry and timing. The Very Large Array in New Mexico, 27 radio dishes working together as a single telescope, observed 3i/Atlas for 48 hours in mid-January. But here's the problem. If the object is transmitting in a directed beam rather than omnidirectionally, we'd only detect a signal if that beam happens to sweep across Earth. It's like trying to spot a lighthouse beam from a ship at sea if you're not in the path of the beam when it rotates past. You see nothing. The Parkes Radio Telescope in Australia, which famously received signals from the Apollo 11 moon landing, added its own observations in late January. Dr. Chenoa Tremblay, who led the Australian effort, employed a different strategy instead of listening for coherent signals. Her team analysed the raw radio noise from 3i/Atlas, looking for patterns, repeating structures or periodicities that might indicate modulation, even if we can't decode the content. We found a possible periodicity at 6.7 hours, Dr. Tremblay reported in a preliminary paper, which interestingly matches one of the rotation periods inferred from the optical light curve. But a 6.7-hour period could also result from natural surface features rotating into and out of view. We can't distinguish between those possibilities with current data. Here's the brutal truth about investigating 3i/Atlas. Every telescope has limitations. JWST can see thermal signatures but can't resolve details smaller than about 30 kilometers at 3i/Atlas's distance, meaning any surface features smaller than a city would be invisible. Radio telescopes can detect signals, but only if they're strong enough and pointed in our direction. Ground-based optical telescopes can track the object's position and brightness, but are limited by atmospheric distortion and can only observe when 3i/Atlas is above the horizon. And here's the worst part, we're running out of time. 3i/Atlas is moving away from us at 180,000 miles per hour. Every day that passes, it gets fainter and harder to observe. By March 2025, it will be so distant that even JWST will struggle to detect meaningful data. By mid-2025, it will fade beyond the reach of our most powerful instruments. And by 2026, it will be gone forever, disappearing back into the interstellar void from which it came. Dr. Paul Callas, an astronomer at UC Berkeley who studies debris disks and exoplanets, put it bluntly in a January op-ed. We have a closing window measured in weeks, not months. Every observation we postpone, every telescope hour we don't allocate to 3i/Atlas is a permanent loss of information. If this object is significant, whether as an unusual natural phenomenon or as something more, we owe it to future generations to gather every scrap of data we can while we still can. So the question becomes, what have we learned from past mistakes? Because this isn't the first time we've encountered an interstellar mystery that slipped through our fingers. October the 19th, 2017. That's the date that should haunt every astronomer who's now watching 3I/Atlas slip away, because on that date, a telescope in Hawaii spotted something that would spark a debate still raging today, and we blew our chance to study it properly. Oumuamua, the name means scout or messenger in Hawaiian, and boy, did it live up to that name. When astronomer Robert Werrick first noticed the object in Pan-STARRS telescope data, he thought it was just another near-Earth asteroid. But within 24 hours, as more observations rolled in, astronomers realised they were looking at something unprecedented, the first confirmed interstellar object ever detected passing through our solar system. The excitement was immediate. Scientists scrambled to point every available telescope at Oumuamua. But here's the problem, and this is critical for understanding why 3I/Atlas matters so much by the time astronomers confirmed what Oumuamua was. It was already leaving, already past Earth, already past its closest approach to the Sun, already accelerating back toward interstellar space. We had weeks, not months, to study it before it faded into the cosmic background forever. The data we managed to collect was fascinating and frustrating in equal measure. Oumuamua was elongated, extremely elongated. Light curve analysis suggested it was at least 10 times longer than it was wide, shaped like a cigar or perhaps a pancake. Nothing in our solar system looks like that. Its dimensions were estimated at roughly 400 metres long by 40 metres wide, about the size of a skyscraper laid on its side. But here's where it gets weird, and why Avi Loeb staked his reputation on the alien hypothesis. Oumuamua accelerated as it left the solar system, just like 3I/Atlas. It deviated from its predicted gravitational trajectory. Dr. Marco Micheli's team measured the acceleration at about 2.5 times 10 circumflex 4 meters per second squared, tiny, but definitely there. For a normal comet, this would be easy outgassing pushes it off course. But Oumuamua showed no visible coma, no tail, no gas emissions detected by any instrument. The Spitzer Space Telescope, which is exquisitely sensitive to the infrared glow of outgassing molecules, saw nothing. Zero. Nada. The problem with Oumuamua, Dr. Karen Meach explained in a 2019 Nature paper, is that every explanation we propose creates new problems. If it's outgassing but we can't see it, then it's outgassing some exotic material we've never encountered. If it's not outgassing, then we need a different mechanism for the acceleration, and none of the natural mechanisms we've proposed quite work. Scientists proposed the hydrogen iceberg theory, that Oumuamua was made of frozen molecular hydrogen, which would outgas invisibly. Problem: hydrogen ice can't exist at temperatures found in most star-forming regions. It would sublimate away long before the object reached us. Others suggested it was a nitrogen iceberg, a chunk of frozen nitrogen blasted off a Pluto-like world orbiting another star. Problem: to produce the observed acceleration through nitrogen outgassing would require losing about 10% of its mass, which should have been visible as a dramatic change in brightness. No such change was observed. Then there was the dust bunny theory that Oumuamua was an incredibly fluffy aggregate held together by weak forces, giving it low density and a high surface area. Problem: an object that fragile should have been torn apart by tidal forces during its close pass by the Sun. It wasn't. Every natural explanation required tweaking the physics, invoking materials we've never seen, or assuming conditions that seemed increasingly unlikely. And that's when Loeb said what everyone was thinking, but nobody wanted to say out loud, what if it's not natural? His 2018 paper with Shmuel Bialy proposed that Oumuamua could be a light sail, a thin, artificial membrane designed to catch stellar radiation for propulsion. The math worked perfectly. A light sail with the right dimensions would produce exactly the observed acceleration without any outgassing. The extreme elongation, that's what a tumbling sail would look like, a flat sheet appearing as a line when viewed edge-on. The backlash was immediate and brutal. Dozens of papers were published attempting to debunk the artificial hypothesis. Some argued the object was too strong to be a thin sail. Others said the tumbling rate would have torn it apart. Doctor. Amaya Morrow-Martin from the Space Telescope Science Institute called Loeb's hypothesis a last resort explanation that ignores more plausible natural alternatives. But here's what bugs me when pressed to provide those more plausible alternatives. Critics kept proposing scenarios that themselves required exotic assumptions. At what point does natural but incredibly weird become less plausible than artificial? The real tragedy of Oumuamua isn't that we couldn't prove what it was. The tragedy is that we weren't ready for it. We didn't have protocols in place, didn't have dedicated telescope time allocated, didn't have spacecraft on standby capable of rapid deployment. By the time the scientific community mobilized, Oumuamua was already beyond the reach of our best instruments. Dr. David Jewett from UCLA, who discovered the Kuiper Belt, conducted a post-mortem analysis of the Oumuamua observations and concluded, "We effectively had one shot at the first interstellar object, and we missed. The data we collected is valuable, but it's nowhere near what we could have obtained with proper preparation. We learned the hard way that these objects don't wait around for us to get organized." So when 2I/Borisov appeared in August 2019, the second confirmed interstellar visitor astronomers were determined not to repeat their mistakes. This time, they were ready. Dozens of telescopes worldwide immediately focused on the object. JWST wasn't operational yet, but Hubble was, and it captured spectacular images showing Borisov with a clear, beautiful tail stretching millions of kilometers behind it. And you know what? 2I/Borisov was boring. Wonderfully, perfectly, reassuringly boring. It looked exactly like a comet from our own Oort cloud. Its spectrum showed water, carbon monoxide, and cyanide standard cometary ices. Its dust composition matched primitive solar system material. Its nucleus was about 1 kilometer across, and it outgassed exactly as models predicted. Brightness variations indicated a rotation period of about 8 hours, completely normal. Dr. Piotr Guzik from Jagiellonian University in Poland analysed Borisov's composition and wrote, "If you placed this comet in our Oort cloud, it would be indistinguishable from native objects. This is what a natural interstellar comet should look like." The relief in the astronomy community was palpable. See, interstellar objects can be completely ordinary. Oumuamua was just a weird outlier, not a sign of aliens. Case closed, except now we have 3I/Atlas. And it's weird in different ways. Not as dramatically elongated as Oumuamua, but with its own set of unexplained behaviours. Minimal outgassing like Oumuamua, but with confirmed cometary ices like Borisov. Unexplained acceleration like Oumuamua, but with chaotic light curves unlike either predecessor. It's almost like 3I/Atlas took notes from both previous interstellar visitors and decided to combine their most puzzling features into one package. Here's what we learned from Oumuamua: you get one chance. One brief window when the object is close enough, bright enough, and positioned well enough for detailed study. Miss that window, and you spend the next decade arguing about ambiguous data because you don't have enough evidence to settle the debate conclusively. We learned that scientific preparedness matters. Dr. Richard Binzel from MIT proposed after Oumuamua that NASA and ESA should maintain a rapid response mission architecture, a spacecraft in permanent readiness that could launch on short notice to intercept interstellar objects. As of 2025, no such mission exists. It's still just a proposal gathering dust while objects like 3I/Atlas fly past. And we learn something uncomfortable about human nature. We're more comfortable with mysteries that remain mysterious than with mysteries that might have revolutionary answers. Because if 3I/Atlas truly is artificial, it doesn't just answer one question, it opens 1,000 new ones, and they're all terrifying. Which brings us to the question that haunts every conversation about 3I/Atlas. If this is a probe from another civilization, what does that mean for us? And more importantly, what does it mean for our place in a universe that might be far more crowded than we ever imagined? Let's talk about the math of loneliness. Because that's really what the Drake equation is, a mathematical framework for calculating whether we're alone in the universe or surrounded by civilizations we simply haven't found yet. In 1961, astronomer Frank Drake scribbled an equation on a chalkboard at the first SETI conference. It wasn't meant to produce a definitive answer. It was meant to organize our ignorance, to identify what we needed to learn before we could answer humanity's oldest question, are we alone? The Drake equation looks deceptively simple. You start with the rate of star formation in our galaxy, about 7 new stars per year. Then you multiply by the fraction of stars that have planets. Then the average number of planets per star that could support life. Then the fraction where life actually appears. Then the fraction where life develops intelligence. Then the fraction that develops technology capable of communication. And finally, you multiply by how long those civilizations survive and transmit signals. When Drake first worked through the calculation in 1961, the estimates were wild guesses. We didn't know if other stars had planets at all. We didn't know how common Earth-like worlds might be. We didn't know if life was a cosmic inevitability or a 1 in a trillion fluke. But here's what's changed in the last 15 years. We've stopped guessing about the first few variables. We know the answers now. The Kepler Space Telescope, operating from 2009 to 2018, stared at 150,000 stars and found planets everywhere. Not around some stars. Around most stars, the data showed that essentially every star in the galaxy has at least one planet. That's 200 to 400 billion planets in the Milky Way alone. Better yet, Kepler found that roughly 20 to 50% of Sun-like stars have rocky planets orbiting in the habitable zone, the distance where temperatures allow liquid water to exist. Dr. Natalie Batala, Kepler's mission scientist, crunched the numbers in a 2013 paper and concluded there are likely 40 billion Earth-sized planets in habitable zones around Sun-like stars and red dwarfs in the Milky Way. 40 billion chances for life. So the first few terms of the Drake equation, we've nailed them down. Planets are common. Habitable planets are common. The universe isn't stingy with the ingredients for life. But the later terms, the ones about life actually arising, becoming intelligent, developing technology, those are still complete mysteries. And that's where 3I/Atlas becomes absolutely crucial to the conversation. Because here's the thing, if 3I/Atlas is a probe, it tells us something profound about that last variable in the Drake equation, the longevity of technological civilizations. Think about it. If a civilization sent 3I/Atlas on its journey 300 light years away, that trip took at minimum thousands of years, possibly tens of thousands depending on its velocity, for that mission to make sense. The civilization had to believe either that they'd still be around when data came back, or that sending probes was valuable even if they wouldn't be there to receive the results. That's a level of long-term thinking and technological stability that humanity hasn't achieved yet. We've existed as an industrial civilization for about 200 years. We've had radio technology for barely 130 years. We've had nuclear weapons for 80 years. Can we make it another 1,000 years without destroying ourselves? 10,000 a million doctor, Frank Drake himself. Before his death in 2022 updated his thoughts on the equation in a final interview. The real unknown isn't whether life exists elsewhere, it's whether intelligence survives its own technology long enough to be detected. Every civilization faces the same test we're facing now. Can they manage their destructive capabilities before these capabilities destroy them? This is called the Great Filter, and it's possibly the most important concept in astrobiology. The Great Filter hypothesis, proposed by economist Robin Hanson in 1996, asks a simple question if intelligent life is statistically likely. Where is everybody? The Fermi paradox, named after physicist Enrico Fermi, who asked, "Where are they?" at lunch in 1950, suggests the galaxy should be teeming with civilizations, yet we see no evidence. No radio signals, no megastructures, no signs of interstellar engineering, just silence. The Great Filter proposes that somewhere between simple chemistry and galaxy-spanning civilizations, there's a barrier, a filter that almost nothing passes through. And the terrifying question is that filter behind us or ahead of us? Maybe the filter is a biogenesis, the jump from chemistry to biology. Maybe life itself is the miracle. And once you have self-replicating molecules, intelligence is inevitable. If that's true, we're probably alone in the galaxy. But we'll survive because the hard part is already behind us. Or maybe the filter is ahead. Maybe civilizations routinely develop to roughly our level nuclear weapons, climate change, artificial intelligence, and then destroy themselves within centuries. If that's true, the galaxy could be littered with the ruins of dead civilizations that never made it past their adolescence. Here's where 3I/Atlas enters the picture with disturbing implications. If 3I/Atlas is a natural comet, it tells us nothing about the Great Filter. The universe continues to be silent, and we continue to wonder whether we're alone or doomed. But if 3I/Atlas is artificial, that changes everything. First, it confirms that at least one other civilization developed technology advanced enough for interstellar exploration. They passed through the filter. They survived their nuclear age, their climate crisis, their AI singularity, whatever challenges they faced. And they did more than survive. They thrived enough to send probes to other star systems. That's monumentally hopeful. It means the filter can be passed. But second, and here's where it gets uncomfortable, it raises the question of why they're not here in person. Why send probes instead of ships? Why observe silently instead of making contact? Dr. Jill Tarter, who spent decades leading SETI research at the SETI Institute, addressed this in a 2018 lecture. If we detect technology rather than biology, if we find artifacts rather than signals, it suggests a universe where interstellar travel is difficult enough that even advanced civilizations rely on automated exploration. Or it suggests they've learned that direct contact is dangerous. Let me ask you something. If you discovered a tribe of uncontacted people living on a remote island, would you land in their village and introduce yourself? Or would you observe from a distance? Maybe leave sensors to monitor their development, and wait to see if they survive contact with the outside world. The zoo hypothesis proposed by radio astronomer John Ball in 1973 suggests that advanced civilizations might deliberately avoid contact with younger civilizations like ours. Maybe there's something like Star Trek's Prime Directive operating on a galactic scale. Maybe they're waiting to see if we pass the Great Filter before revealing themselves. Or maybe, and this is darker, they're not avoiding us. Maybe they're just gone. Maybe 3I/Atlas is an ancient probe from a civilization that died out millions of years ago, still executing its programming long after its craters turned to dust. A ghost ship sailing through the cosmos with no one home to read the data it collects. Doctor, Milan Cirkovic, an astrophysicist who studies existential risk, calculated in a 2008 paper that if interstellar probes last millions of years, but civilizations only last thousands, the galaxy could be full of orphan technology, functional but purposeless, observing but never reporting back. That's the scenario that really keeps xenobiologists up at night. Not that we're alone, not that aliens are hostile, but that we're surrounded by evidence of civilizations that failed, that didn't make it through the Great Filter, and their probes are still out here, silently witnessing our own struggle to survive the next century. Here's the statistical reality: our galaxy is 13.6 billion years old. Earth is 4.5 billion years old. Life on Earth has existed for about 3.8 billion years. But technological civilization just 200 years. We're newborns. If other civilizations arise at random intervals throughout the galaxy's history, then most of them are either billions of years older than us or haven't emerged yet. The civilizations that are billions of years ahead of us should be everywhere, building Dyson spheres and restructuring solar systems. But we see none of that, which suggests either intelligence is incredibly rare, or it doesn't last long enough to become galaxy-spanning. The Great Filter took them out. And if 3I/Atlas is evidence that civilizations do arise and do send probes, but we still see no signs of thriving galactic empires, then the filter might not be behind us at all. It might be sitting in our near future, waiting to test whether humanity has what it takes to join the survivors or become another cautionary tale floating through space, silently observed by our own orphaned probes. But before we spiral into existential dread, let's ground ourselves in something important: the difference between scientific inquiry and wishful thinking. Because the way we approach this mystery matters as much as the answer itself. Here's something that might surprise you scientists, and the public want completely different things from the 3I/Atlas story. And understanding that gap is crucial to making sense of why this controversy has become so heated. When a major news outlet runs a headline like "Scientists detect possible alien probe in solar system," millions of people click immediately. Their hearts race. They imagine contact, communication, maybe even spacecraft landing on the White House lawn. They want a definitive answer, and they want it now. But when scientists read that same headline, they cringe. Because in science, the words possible and probable exist in entirely different universes, and the gap between them is filled with years of research, peer review, and a methodology specifically designed to prevent us from fooling ourselves. Let me show you how this plays out in practice. In August 1967, graduate student Jocelyn Bell was analysing radio telescope data from Cambridge when she noticed something bizarre: a signal pulsing with impossible regularity. Exactly once every 1.337 seconds. The precision was so perfect, so artificial looking, that the team half-jokingly labelled it LGM1 Little Green Men 1. For a few weeks, the possibility that they detected an alien beacon was genuinely on the table. The signal was coming from a fixed point in space. It didn't match any known natural phenomenon, and that clockwork precision, nothing in nature behaves that consistently. But Bell and her advisor, Anthony Hewish, didn't call a press conference announcing aliens. They kept observing. They found 3 more similar signals from different parts of the sky. And eventually, they realized they'd discovered pulsars, rapidly rotating neutron stars whose magnetic fields sweep past Earth like cosmic lighthouses. Completely natural, completely explainable by physics. No aliens required. Bell and Hewish won the Nobel Prize in Physics for that discovery in 1974. Not because they found aliens, but because they found something nature does that nobody predicted. That's how science works. You follow the evidence wherever it leads, even when it leads somewhere less exciting than you hoped. Now fast forward to 2007. Astronomers detected fast radio bursts, millisecond-long blasts of radio energy from distant galaxies, releasing more energy in 1,000th of a second than our Sun produces in a year. Once again, the precision and intensity seemed artificial. Once again, headlines screamed about possible alien signals. Dr. Duncan Lorimer, who discovered the first FRB, had to spend years fighting back speculation. Every time we detect something we don't immediately understand, he told Nature in 2013, a certain segment of the public and media jumps straight to extraterrestrial intelligence. But extraordinary claims require extraordinary evidence. An unexplained signal is not evidence of aliens. It's evidence that we need to do more astronomy. By 2024, we detected thousands of FRBs and traced them to extreme astrophysical phenomena, probably magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. Again, nature doing something incredible. Again, no aliens. Can you see the pattern here? Nature is weird. Nature is creative. Nature produces phenomena that seem impossible until we understand them. And the public's eagerness for alien explanations often runs far ahead of what the data actually supports. This is where 3i/Atalus sits right now, caught between scientific caution and public excitement. And it's where media coverage becomes genuinely problematic. Here's how the media amplification cycle works. A scientist publishes a paper saying object displays anomalous behavior requiring further study. A university press office, hungry for attention, issues a release saying mysterious object baffles scientists. A news website competing for clicks runs with "Could this be an alien probe?" A social media influencer, chasing engagement, posts "Alien spacecraft confirmed." And suddenly, millions of people believe there's definitive proof when the original scientist was simply saying, "This is weird and we should investigate." Dr. Katie Mack, a theoretical astrophysicist who studies how science communication goes wrong, wrote about this in her 2020 book, The End of Everything. The distance between "we don't know what this is" and "it must be aliens" is vast. But headlines compress it to nothing. The problem isn't that people are excited about the possibility of alien life, that excitement is wonderful and justified. The problem is that we've trained them to expect certainty from science when the entire point of science is managing uncertainty. Let me be clear about what scientists actually know about 3i/Atlas. It's an interstellar object with properties that don't perfectly match standard cometry models. That's it. Everything beyond that statement is hypothesis, speculation, or wishful thinking. What scientists don't know whether the anomalies represent new natural physics we haven't discovered, measurement errors we haven't identified, or something genuinely artificial. They don't know because the data isn't conclusive yet. And here's the key point: saying "I don't know" is not a weakness in science. It's the most honest and valuable thing a scientist can say. Dr. Sarah Seeger from MIT, who specializes in exoplanet characterization and biosignatures, put it perfectly in a January 2025 interview with Scientific American in my field. "We've learned to be comfortable with ambiguity. We detect an atmospheric signature that might be a sign of life, or might be geology, or might be an instrument artifact. We don't immediately jump to the sexiest interpretation. We say, here's what we observe, here's what it can mean, here's what we need to learn next. That patience is essential." But the public doesn't want patience. The public wants answers. And social media rewards certainty, not nuance. I've seen dozens of YouTube videos with titles like "Scientists Prove Alien Probe Visiting Earth," with millions of views. Meanwhile, careful, measured analyses with titles like "Analyzing the Photometric Properties of Interstellar Object 3i/Atlas" get a few thousand views, mostly from other scientists. The algorithm doesn't reward accuracy, it rewards emotion. This creates a dangerous feedback loop. Scientists become more cautious about communicating anything that might be misinterpreted. The public perceives that caution as scientists hiding something or being close-minded. Trust erodes, and when scientists do need the public to pay attention to something genuinely important, climate change, pandemic preparedness, asteroid impacts, they've already lost credibility with the very people they're trying to reach. Dr. Neil deGrasse Tyson addressed this dynamic in a February 2025 Star Talk podcast. The scientific method is specifically designed to protect us from our own biases and wishful thinking. When I want something to be true and I hope aliens are real, that's exactly when I need to be most skeptical of evidence suggesting they are. Because I know my brain will find patterns that aren't there, significance that doesn't exist. Science is the tool we invented to save us from ourselves. Here's a concrete example of how this plays out. Remember those warm spots on 3I/Atlas that JWST detected in media coverage? They became unexplained heat sources suggesting internal power generation. In scientific papers, they're described as thermal anomalies requiring additional modelling to determine whether they're consistent with differential sublimation rates or potentially indicate non-uniform composition. Same data, completely different framing. One version suggests aliens, the other suggests we need more data. Both are technically accurate descriptions, but only one is scientifically responsible. And here's what really matters: being wrong is expensive in science. If you publish a paper claiming something extraordinary and you're wrong, your career suffers. You lose funding, other scientists stop taking your work seriously. So the incentive structure pushes toward conservatism, toward waiting for bulletproof evidence before making claims. That's why Avi Loeb's willingness to propose the alien hypothesis is so remarkable and so controversial. He's risking everything on the possibility that he's right. And if he's wrong, history won't remember the nuance of his argument. It'll remember that Harvard astronomer who thought a space rock was a UFO. But here's the flip side. What if the cost of excessive caution is missing the most important discovery in human history? What if the evidence is sitting right in front of us? But we're so afraid of being wrong that we refuse to seriously consider what it might mean. That's the tightrope scientists walk every single day. And with 3I/Atlas racing away from us at 180,000 miles per hour. The decision about when to stop being cautious and start being bold is happening right now, whether we're ready for it or not. So here we are. It's February 2025, and 3I/Atlas is already 2.8 astronomical units from the Sun, about 260 million miles and accelerating away. Every passing day makes it dimmer, colder, harder to observe. The window is closing, fast, and scientists are faced with a brutal choice: keep observing until they're absolutely certain what they're looking at, or accept that certainty might not be possible before the object disappears forever. Let me put this in perspective. Right now, 3I/Atlas is receding at roughly 4 million miles per day. By March 2025, it will be beyond the orbit of Mars. By June, it'll pass Jupiter's orbit. By the end of 2025, it will be farther from the Sun than Saturn, and even JWST will struggle to resolve it. By 2027, it will fade into the cosmic background noise, indistinguishable from the billions of other faint objects in deep space. We're not going to get another chance. This isn't like studying a star or galaxy that will still be there in 100 years when we build better instruments. This is a one-time opportunity with a countdown timer attached. Dr. Paul Callas from UC Berkeley calculated the observation timeline in a February preprint paper. Based on current trajectory and fade rates, we estimate useful photometric data collection will cease by August 2025, and spectroscopic analysis will become prohibitively difficult by October 2025. After that date, 3I/Atlas becomes effectively unobservable with current technology. 8 months? That's how long we have to answer one of the most important questions humanity has ever asked. So what would it take to definitively prove 3I/Atalus is a comet, and what would it take to prove it's artificial? Let's start with the natural hypothesis. To conclusively confirm 3I/Atlas is a comet, scientists need to explain every anomaly with conventional physics. That means first, identify the composition that produces minimal outgassing but still explains the observed acceleration. Several teams are working on this. Dr. Daryl Seligman from Cornell proposed in a January 2025 paper that 3I/Atlas might be made of super-volatile ices materials like carbon monoxide or nitrogen that sublimate at extremely low temperatures, producing invisible gas that wouldn't show up in optical observations but could still create thrust, the problem. To test this hypothesis, you'd need to detect those gases directly using sensitive infrared spectroscopy during specific observing windows. JWST has limited observation time. Astronomers compete for every hour, and 3I/Atlas isn't the only scientific priority. As of February 2025, JWST has allocated 26 additional hours to 3I/Atlas observations, spread across March and April. That's it. Second, explain the chaotic light curve with a plausible shape and rotation state. Dr. Wes Fraser's team is building 3D models attempting to match the observed brightness variations with irregular but natural shapes. They've proposed that 3I/Atlas might be a contact binary, two objects stuck together like a cosmic peanut with different surface compositions on each lobe. Again, the problem is data. To confirm this model, they need continuous photometric monitoring across multiple rotation periods, but 3I/Atlas is only visible from certain locations on Earth at certain times. And weather, telescope scheduling conflicts, and the moon's brightness interfere. Getting complete coverage is nearly impossible. Third, explain those unexplained spectral features at 3.8 and 4.2 microns. This requires either laboratory experiments creating exotic ice phases under interstellar conditions, or detection of the same features on other objects, proving they're natural rather than unique to 3I/Atlas. Both approaches take time we don't have. Here's the reality: proving something is natural is often harder than proving it's artificial, because nature is allowed to be arbitrarily weird. There's no limit to how strange natural phenomena can be, so you can always propose one more exotic scenario, one more unlikely combination of factors that might explain the data. Now let's talk about the artificial hypothesis. What would it take to prove 3I/Atlas is technology option 1? Detect a signal. If 3I/Atlas transmits anything radio waves, laser pulses, modulated neutrinos that shows intelligent structure, game over, proof positive. The Galileo project has dedicated radio telescope time through April 2025 specifically searching for this. So far, nothing. But absence of evidence isn't evidence of absence, especially if the probe is dormant or transmitting in ways we can't detect. Option 2. Observe geometry inconsistent with natural formation. If high-resolution imaging reveals straight edges, right angles, or repeated patterns, that's essentially impossible to explain naturally. The problem 3I/Atlas is too far away. Even with JWST, the angular resolution is about 30 kilometers at this distance. Any manufactured details smaller than a city would be invisible. Option 3. Detect materials or isotopic ratios impossible in natural settings. This requires spectroscopy sensitive enough to measure not just what elements are present, but the ratios of different isotopes. Certain isotopic signatures would scream industrial process rather than natural formation. But this level of precision needs the object to be much brighter than it currently is. Do you see the problem? We're trying to prove something extraordinary with instruments barely adequate for the task, and we're running out of time. Which brings us to the question that should have been asked on December 13th, 2024, the day after 3, I/Atlas was discovered. Should we go there? I'm talking about a spacecraft mission. An actual probe sent to intercept 3I/Atlas. Get close enough to photograph it, analyze it, maybe even touch it. Is it possible? Let's look at the physics. 3I/Atlas is currently about 400 million miles from Earth and moving away at 50 miles per second. To catch it, you'd need a spacecraft capable of not just reaching that distance, but matching its velocity. NASA's New Horizons probe, the fastest spacecraft ever launched, would take years to reach that distance, by which point 3I/Atlas would be billions of miles farther away. Dr. Kelsey Singer from the Southwest Research Institute ran trajectory calculations in January 2025. A rendezvous mission launched with current technology would need approximately 8 to 10 years to intercept 3I/Atlas. Assuming we use gravitational assists from Jupiter, by that time, the object would be 15 to 20 astronomical units from the Sun, farther than Uranus, making solar power impractical and communication significantly delayed. But here's the thing, it's not impossible, just expensive and difficult. The European Space Agency's Comet interceptor mission, scheduled to launch in 2029, is specifically designed for this scenario, sitting at a gravitational parking spot until an interesting comet appears, then launching on short notice to intercept it. But Comet Interceptor won't be ready for years, and 3I/Atlas won't wait. There's another option. Theoretically, Project Lyra, proposed by the Initiative for Interstellar Studies in 2017 after Oumuamua's discovery, outlines a mission architecture using solar oberth maneuvers diving close to the Sun to gain a massive velocity boost combined with advanced ion propulsion. The calculations show it could theoretically catch 3I/Atlas within 5 to 7 years. Cost estimates somewhere between $500 million and $1 billion. About the same as a single Mars rover mission. Dr. Andreas Hein, who leads the Project Lyra team, made the case in a February 2025 Nature Astronomy editorial. We're watching potentially the most significant object in human history accelerate away from us. And we're doing nothing but watching through telescopes. If there's even a 5% chance this is artificial technology, the expected value of investigating directly is incalculable. We'd spend $1 billion on a particle accelerator experiment with far less potential impact. But here's the reality: space agencies don't work on 3-month timelines. Missions take years to plan, design, fund, and approve. By the time committees meet, budgets get allocated, and spacecraft get built. 3I/Atlas will be a faint memory fading into interstellar space, so we're left with telescopes, limited observation time, ambiguous data, and a closing window, which means the answer to whether 3I/Atlas is a comet or a probe might not come from definitive proof. It might come from a decision about what we're willing to believe based on incomplete evidence. And that decision, whether we're ready for it or not, is going to define how we understand our place in the universe for the next generation. So let's play this out. Let's imagine 2 futures, 2 versions of how the 3I/Atlas story ends, and you tell me which one you'd rather live in. Future 1. It's a comet. By September 2025, after months of intensive observation, a team led by Dr. Michelle Bannister publishes a comprehensive paper in Nature. They've identified the exotic ice composition, a mixture of carbon monoxide and methanol with trace organics that explains the minimal outgassing. They've modelled the tumbling rotation and irregular shape that produces the chaotic light curve. They've matched the spectral anomalies to complex organic molecules formed in the deep cold of interstellar space. The unexplained acceleration outgassing from supervolatile ices on the object's night side, invisible in optical wavelengths but detectable in sensitive infrared observations. The math works, the physics checks out. Every anomaly has a natural explanation that, while exotic, doesn't require invoking new laws of nature or extraterrestrial engineers. 3I/Atlas was just a comet. A weird one. Sure. One of the strangest natural objects we've ever observed. But ultimately just frozen chemistry following the rules of thermodynamics and orbital mechanics. The scientific community breathes a collective sigh of relief. Papers are published, careers advance, the data gets archived, and 3I/Atlas fades into the background of astronomy history as that one interstellar comet that briefly made people wonder. In this future, we learned something valuable about cometary diversity and interstellar chemistry. We improved our detection methods and observation protocols. We got better at studying fast-moving objects in real time. All good things. All incremental progress in our understanding of the universe. But be honest with yourself, how much would this discovery change your life? Would you think about 3I/Atlas a year later? 5 years later? Or would it fade into the background noise of interesting space facts, alongside pulsars, quasars, and the occasional news about Mars rovers, future to its technology? Now imagine this. In March 2025, the Breakthrough Listen project detects a 12-hour signal from 3I/Atlas, faint but structured. Not random noise, not natural radio emissions. A repeating pattern at 1.42 GHz, the frequency of neutral hydrogen, a universal marker any technological civilization would recognize. The signal contains no obvious message, just a beacon. A ping saying, I am here, I am not natural. Within 24 hours, every major telescope on Earth and in orbit redirects toward 3I/Atlas. The data comes flooding in. High-resolution infrared imaging reveals geometric patterns too regular to be natural hexagonal panels covering 40% of the surface. Spectroscopy detects titanium-aluminum alloys with isotopic ratios impossible in stellar nuclear synthesis. JWST captures thermal variations consistent with internal power generation. The evidence becomes overwhelming. This is technology, manufactured, sent here deliberately or drifting here by chance, but definitely artificial. What happens next? First, pandemonium. Not panic, humans are surprisingly good at processing world-changing news, but a complete reorientation of priorities. Governments convene emergency sessions. The UN activates protocols for extraterrestrial contact. Every news network on Earth leads with the same story for weeks. Social media explodes with a mix of wonder, fear, excitement, and conspiracy theories. But beneath the chaos, something profound shifts. Dr. Frank Drake, in that final interview before his death, said something haunting. The moment we confirm we're not alone, nothing will ever be the same. Not religion, not philosophy, not politics, not art. Every human endeavour will be coloured by the knowledge that intelligence exists beyond Earth. We'll never be able to unknow it. Think about what that means. Every person alive would know with certainty that we're not the only ones. That intelligence, technology, and curiosity exist elsewhere. That the universe isn't a sterile wasteland, but a place where minds emerge, build, and explore. Would we still fight wars over borders when we know there are civilizations out there that view our entire planet as a single pale blue dot? Would we still destroy our environment when confronted with evidence that technological species can survive for millennia? Would we still treat science as optional when faced with proof that understanding the universe is the path to unimaginable capabilities? Maybe. Humans are stubborn, but I suspect the shift would be seismic. Carl Sagan wrote in Pale Blue Dot, The Earth is a very small stage in a vast cosmic arena. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. He wrote that in 1994, just from seeing a photo of Earth from 4 billion miles away, imagine the psychological impact of confirmed extraterrestrial technology passing through our solar system. Here's what I think would happen, and I'm basing this on conversations with sociologists, psychologists, and historians who've studied paradigm shifts in human thinking. Initially, there'd be fear. Not of Invasion 3I/Atlas would be leaving, not arriving, but existential fear. The fear of cosmic insignificance. The fear that we're children in a universe of adults. Some people would retreat into denial, others into nihilism. But gradually, something else would emerge, hope. Because if 3I/Atlas is a probe, it means someone out there solved the problems we're struggling with. They survived their technological adolescence. They didn't destroy themselves with nuclear weapons or climate catastrophe or AI gone wrong. They made it through. And if they made it, maybe we can too. Dr. Jill Tarter, reflecting on decades of SETI work there, told the New York Times in 2019, "The most important thing about detecting extraterrestrial intelligence isn't what we'd learn about them, it's what we'd learn about ourselves. We'd learn that the great filter can be passed. We'd learn that intelligence isn't a cosmic dead end. We'd have proof that it's possible to build a civilization that lasts." That's what's really at stake with 3I/Atlas. Not just the discovery itself, but the permission it would give us to believe that our future doesn't have to end in extinction. So which future do you want? Here's the uncomfortable truth you don't get to choose. Reality doesn't care about our preferences. 3I/Atlas is either natural or artificial, and no amount of hoping or fearing will change what it actually is. But here's what you do get to choose how you respond to uncertainty. You can dismiss the possibility of artificial origin entirely, retreating into comfortable assumptions that we're alone and everything unexplained has a boring natural explanation. That's safe. It protects you from disappointment. Or you can hold space for genuine uncertainty, acknowledging that we don't know yet, that both possibilities remain open, and that the answer, whatever it is, will teach us something profound about the universe we inhabit. Carl Sagan, who spent his entire career balancing skepticism with wonder, gave us the perfect framework. Extraordinary claims require extraordinary evidence. But he also said absence of evidence is not evidence of absence. And most importantly, somewhere, something incredible is waiting to be known. 3I/Atlas might be that something, or it might be a frozen chunk of ancient ice teaching us about chemistry we didn't understand. Either way, the fact that we're even asking the question that we have the technology and curiosity to investigate is itself extraordinary. We're living through a moment where humanity is sophisticated enough to detect interstellar objects, analyze their composition, and seriously consider whether we're looking at technology from another world. Think about that. 100 years ago, we didn't know other galaxies existed. 50 years ago, we didn't know if other stars had planets. 20 years ago, we'd never detected an interstellar object. And now we're watching 3I/Atlas disappear into the cosmic dark, racing to gather every scrap of data before it vanishes forever, knowing that the answer might redefine everything. So, here's my question for you, the one that matters more than whether 3I/Atlas is a comet or a probe. Are you paying attention because moments like this, where the boundary between known and unknown gets tested in real time, don't come around often? This is what it looks like when science happens at the edge of human knowledge. Messy, controversial, uncertain, thrilling. And whatever we learn from 3I/Atlas, whether it confirms our loneliness or shatters it forever, we'll have learned it together. staring up at the same sky our ancestors watched, asking the same questions they asked, but finally with the tools to find answers. The universe is vast. It's ancient. It's stranger than we imagine, and perhaps stranger than we can imagine. But it's not silent. It's speaking to us through light, through gravity, through the trajectories of objects that travelled unimaginable distances to pass through our small corner of existence. 3I/Atlas is speaking. The only question left is whether we're listening carefully enough to understand what it's saying.